Welcome back of the massive open online course on advanced analytical techniques. In the previous lecture, we have gone through the concept of spectroscopy as well as the difference between an absorption as well as emission spectroscopy. We have briefly discussed about the components of atomic emission as well as atomic absorption spectroscopy. In this lecture, we'll talk in more detail about the atomic absorption spectroscopy. It is one of the most widely and simple method for analysis of metals present in aqueous media. Specifically, it is used for metals like chromium, nickel means the transition metals, alkali metals, alkaline earth metals, and even for some metalloids. In the periodic table, around 50 to 55 elements can be analyzed by atomic absorption spectroscopy. As I said, it is one of the simplest method, but it is also quite reliable, so it is widely used. The light which is being absorbed, or I should say the amount of light which is absorbed, is directly proportional to the concentration of atoms of a given element present in the vaporized state. As you can see in this figure, we have an atom, we have a nucleus where we have protons and neutrons as nucleons, they are present, and the electrons which is present in the outermost orbit. Upon absorption of energy from UV or visible region, the electrons, this electron is excited to the higher levels. Means from the outermost orbit which is filled, it is moving to the vacant orbit from E0 to E1, and it may also go from E0 to E2 by the absorption of energy. Then this wavelength is basically missing from the spectrum, and when our detector detects the transmitted light based on this missing wavelength, we can identify the type of atom, because each and every atom has its characteristic spectrum. This concept was given by G.R. Kirchhoff in 1959, that each and every pure element, pure atom, has its own characteristic absorption, and the amount of light absorbed is directly proportional to the concentration of the element. This basically serves as the principle of atomic absorption spectroscopy. Now, in this figure, you can see that I have shown you the different levels. This is the ground state represented by E0, and then we have different excited states, the E1, E2, and E3 and E4. And for example, if the electrons are excited from E0 to the highest available energy level, means the E4, and here you can see the absorption occurs at 202.2 nanometers, while from E0 to E1, the absorption occurs at a higher wavelength. What does it mean? This means that for a transition from E0 to E1, since the energy gap is small, light of lower energy is needed. And light of lower energy means it has a higher wavelength, because we have this equation Hc by lambda from the Planck's equation. The energy is inversely proportional to the wavelength. So, if the energy gap is small, we need light of longer wavelength to excite the electrons from the ground state to that particular excited level. As we keeps on increasing the energy level from E1 to E2 and to E3, the energy requirement is going up, and since the energy requirement is going up, we need light of shorter wavelength. So, from here, the takeaway is, the lower the energy gap, the light radiation of longer wavelength is needed for excitation. This figure is particularly for an element called lead, and for lead, we can have in its spectrum different types of wavelength. Although most of the time we use the energy or the wavelength responsible for transition from E0 to E1, but we may also get transitions from E0 to E3 and E2 and E3, which can also be used to check the sensitivity of the instrument, as well as we may have more detailed information. this periodic table here, in this table you can see all these blue color elements, they can be detected with the help of atomic absorption spectroscopy. And as I said, around 50 to 55 elements comprising mainly of metals and few metalloids can be detected with the help of atomic absorption spectroscopy. We have here the alkali metals, alkaline earth metal, and majority of the transition metals that can be detected, and various other metals can be analyzed with the help of AAS technique. Now comes to the history of atomic absorption spectroscopy. The technique was based mainly on the pioneering work of Alan Walsh in 1950, although it was fully developed and used by two other scientists, Robert Wilhelm Bunsen and G.R. Kirchhoff. G.R. Kirchhoff is the scientist who theorized that and who proved that each and every pure component has its own characteristic spectrum. So they together work on this technology and they develop the atomic absorption spectroscopy. But the instrument is based on the work of Professor Alan Walsh. He was a scientist at Commonwealth Scientific and Industrial Research Organization, CSIRO. The principle now comes to the principle of atomic absorption spectroscopy. The atomic absorption spectroscopy's principle lies upon the fact that the amount of light that is being absorbed at a particular wavelength is proportional to the concentration of atoms in vaporized state, which means that when we have a sample tube, we have sample over there, we are exciting those sample with the help of a light radiation, then the amount of light depends upon the concentration of the atom or the concentration of the analyte atoms. Higher the concentration, we have more amount of absorption resulting into the transmitted light of lower intensity. However, if the concentration is low, there will be lesser absorption and the intensity of transmitted light would be high. One more thing which is worthy of mentioning here is that in case of atomic absorption spectroscopy, we do not directly excite an aqueous sample. We take the aqueous sample and we use a component called as nebulizer that converts this aqueous sample into an aerosol. Just like the perfume which we use at home, we have a liquid sample over there, but when we press the button and when we apply that perfume, it always comes out in the form of an aerosol. Because if we directly use an aqueous sample, it would be difficult to convert the sample into individual atoms. And since the technique is based upon the analysis of individual atoms rather than whole compounds, we need to first of all atomize the sample. For atomization, instead of using the liquid sample directly, we take the sample which is in liquid form. First we convert it into an aerosol, and then from that aerosol we heat the sample so that it gets converted into individual atoms. Then those atoms are being excited by giving them incident radiations, resulting into an absorption spectrum. This is the basic component. This is the basic concept of this spectroscopy. When the atoms are excited, the free electrons are transferred to higher energy by the absorption of light of UV or visible region. So in this way, an absorption spectrum is formed by atomic absorption spectroscopy. So once again, so these are the main components of an atomic absorption spectroscopy, or popularly called, or you may call it as AAS. We have a nebulizer, then atomizer, we have a light source, monochromator, detector, and amplifier. This is a flow sheet which represents a light source. The hollow cathode tube is used as a light source, and you can see here we have a liquid sample in a container. but rather than using this liquid sample directly, we connect this with a nebulizer, and there is a pipe from nebulizer that is coming into this solution, and then the nebulizer sucks in the sample, mix it with an oxidant, like it may be oxygen gas, it may be nitrous oxide, and then mix it with fuel as well, and then convert it into an aerosol. Then that aerosol, so here we have aerosol which is being converted by this nebulizer by sucking this sample from the container. Now we have aerosol over here, the small droplets of liquid sample in fuel gas as well in fuel gas as well as an oxidant. Then they entered into the atomizer. The purpose of atomizer is to burn these samples, it is to distribute these samples into individual atoms. Then these atoms absorb light radiation that is coming from this side, and they undergo excitation. Some wavelengths are being absorbed, and the transmitted light then passes through a monochromator and finally detected by our detector, which is the photomultiplier tube. Then we have an amplifier which amplifies the signal. For example, if the signal is this such small, is this, if for example if this signal is this small, it converts and amplifies the signal, creates it into an amplified signal, and that signal can be easily presented you on the recording device, or you can say the display device such as computer. Now we'll individually discuss all these components in detail. So nebulizer, as I said, the job of the nebulizer is to convert the sample into an aerosol. So a liquid sample is converted into an aerosol with the help of this nebulizer. This nebulizer also controls the flow of the sample into the atomizer. For example, if the sample is running at a very fast rate, then that means a high amount of sample entered into the atomizer. If the volume of the sample is high, then there are chances that it may extinguish that atomizer, which means that, for example, if you are lighting a flame for heating or atomizing the sample, and if more volume of the sample is coming, it may extinguish that flame, or it may reduce the temperature of the flame. So the flow rate of the sample should be not very slow, and so the flow rate of the sample should not be too high or too low. This is the job of the nebulizer. So our nebulizer controls the flow rate and also convert the sample into an aerosol. So what does it do? It mixes the sample, because the sample is coming, there is a conical flask, we have sample over there, then we have a nebulizer as I have shown you in the previous slide, then there is a pipe which sucks in the sample. Here the nebulizer has some motors fitted. Then this nebulizer mix the sample with fuel and oxidant. As you all know that for lighting a flame, we not only needed a fuel, we also need an oxidant. Just like we have at our home the LPG cylinders, we use LPG gas, which is a mixture of butane and propane, but we also need oxygen to lit that flame. Similarly, in this technique also, we may use hydrogen gas, we may use acetylene gas. Acetylene gas is quite preferable for using AAS technique. So we need some oxidant as well. That could be air, that could be pure oxygen, or on nitrous oxide, which oxidizes the sample, resulting into complete combustion of the fuel, so as to give very high amount of heat. Because if the combustion or the heating or the burning of the fuel is not proper, if it is not properly burnt, then the energy released is not as expected, and there are chances that all the molecules will not be converted into individual atoms. And since atoms are not formed, there will be no absorption, resulting into a spectrum which is not the actual characteristic spectrum of that particular compound. So it will hamper the analysis. Therefore, for a reliable analysis, we need a nebulizer which is giving a controlled flow rate and which is converting sample into an aerosol properly, and also we need an atomizer that can provide efficient thermal energy to completely atomize the sample. So our nebulizer mix the sample with fuel, which is most of the time acetylene gas, as well as oxidant, sometimes air, but it is better to use pure oxygen or nitrous oxide. Now this now the nebulizer, it has a small orifice over here, the sample is injected, and finally when it is released, what it does, it creates a negative pressure at the outside of this orifice. When this pressure is negative and we have high pressure over here, then this high pressure will inject the sample with very high force, and the sample is immediately converted into an aerosol, because high pressure always pushes the sample towards the low pressure, and outside this orifice we do not have a low pressure but we have a negative pressure. That means it is pushed at very high force, and it is immediately converted into small droplets of the sample in small droplets along with fuel and oxygen, which can be easily burnt and atomized. So this causes the mixture to be pumped, and this aerosol is then pumped into the burner at high pressure in the form of aerosol, and this evenly distributed aerosol is immediately burnt, effectively converting that sample into individual atoms. Now this is the inside image of a nebulizer, and nebulizer maintain a laminar flow. I hope that you all are aware with laminar flow. Laminar flow, there are two types of flow of a liquid. One is called a turbulent flow, where the particles can go anywhere, the velocity is even not constant. But in laminar flow, the velocity of all the particles, all the droplets is constant, and they are moving in a straight line. The velocity profile is like this. The droplets or the layers that are towards the surface of the pipe, they have lower velocity due to friction from the walls, while the layer which is present in the middle, they have very low friction, so their velocity is always high. The velocity profile is always like this in a laminar flow. So a controlled laminar flow is maintained by the nebulizer, and the sample enters from here, and excessive sample is drained by this waste pipe. Now this nebulizer, we have fuel and we have oxidant. The purpose of the oxidant is to oxidize the fuel, and here we have auxiliary oxidant and we have nebulizer oxidant. Auxiliary oxidant burns the fuel, while nebulizer oxidant is used to convert sample into an aerosol. Then, as I said, it creates a negative pressure over here. So the sample is injected at very high pressure into this atomizer, where the sample is burnt. This controlled flow rate and proper distribution of an aerosol help us to increase the reproducibility, because if the sample is evenly distributed aerosol, it will not affect the flame, it will not affect the temperature of the flame. Also, a long path length is used so that we may have efficient sample, so that we may have a proper flow rate maintained that can increase the sensitivity of the technique. The aerosol droplets that fall outside the flame, they are connected into the waste container, which is placed at the bottom of the nebulizer. We have a waste container placed at the bottom of the nebulizer, where the excessive sample we drained out from here, and also if we have some aerosol droplets that falls outside, they are being collected in this waste container. Now the second main component of the atomic absorption spectroscopy is the atomizer, or we can say is the heat source. The job of this atomizer is to convert the sample into individual atoms. So there are three steps that are being carried out, or that there are three, I should say, there are three functions of this atomizer. The first function of this atomizer is desolvation, because this, as I said, the sample is in liquid form earlier, means our analyte is dissolved in some solvent, then that solvent is finally, then that liquid is finally taken by the nebulizer, where it is mixed with fuel as well as oxidant to form an aerosol. Now this means that we have aerosol which contains liquid sample in a gas. So we still have the sample present in solvent molecules in the form of droplets distributed in this aerosol. So the first function or the first job of this atomizer is to remove the solvent, and therefore the step is called as desolvation. In this step, the solvent is evaporated, uh, it is removed, and a dry sample is immediately formed. So the first job is to remove solvent, removal of solvent. Now we get a dry sample. Now this dry sample, so the first job is to create, so the first job is to remove the, so the first job is to remove the solvent. Once the solvent is removed, the sample is obtained in dry form. Then this dry sample is vaporized. Then this dry sample is vaporized because we need it in vapor form. It gets converted into gaseous molecules, and then those gaseous molecules are broken down into individual atoms. So first we have dissolution, means the removal of solvent. Then we have vaporization, which converts the dry sample to a gas, and finally we have the atomization. Finally we have the atomization, where the molecules converted into individual atoms. Now these atoms are present in vaporized form, and thus they are ready for excitation with the help of light coming from the light source. Clear, students? Now in these two steps, the nebulizer and atomizer, the sample which is initially present in the form of a solution, it is being sucked up, it is being converted into an aerosol, finely divided aerosol which contains liquid drops in a gas. Then they enter into the atomizer, where they are heated at high temperature. In the very first stage, the solvent molecule, in the very first stage, the solvent is evaporated, resulting into a dry sample. Then that dry sample is vaporized to get vaporized atoms. Then that dry sample is vaporized to get vaporized sample. And at this stage, the vaporized sample, means the molecules that are present in vapor form, they are atomized, or they are dissociated into individual atoms, and now these atoms are ready for absorption of light. So these two components, the nebulizer and atomizer, plays most important role. It doesn't mean that only the light source or the detector is important. Each and every component is important. If the nebulizer is not doing its job properly, if the nebulizer is not converting the sample properly, what would happen? If the aerosol is not properly formed, or the droplets are not evenly distributed, large volume of sample is directly injected into the atomizer, which will create the temperature of the atomizer to drop, or it may extinguish the atomizer. Therefore, nebulizer is very important. The flow rate control as well as the formation of aerosol, both are very important. Similarly, the atomization is also very important. The heat source or the thermal energy that we are providing should be stable and should be effectively able to convert the sample into individual atoms in vaporized state. For that, we generally use two common types of atomizer. One is called as the flame atomization or direct aspiration technique, in which we lit a flame, and the atoms that are in which we directly lit the flame, and the aerosol that is coming from the nebulizer, they directly entered and undergo atomization, means desolvation, and the aerosol that enter undergo atomization, means the desolvation, vaporization and dissociation. And we also have graphite furnace. They are electrical thermal units which uses electrical discharge to convert sample from liquid air, which converts the sample from aerosol to vaporized atoms, vaporized individual atoms. So this is a flow sheet representing the two processes of nebulization as well as atomization. In this, as I said, you take a solution of the analyte, then that analyte is converted into a spray, an aerosol, just like we use our perfumes or various other things that are basically stored in the form of a liquid at high pressure, and they are released in the form of an aerosol. So this is an aerosol. In the same way, our sample from the solution form is taken up by the nebulizer. It is mixed with the fuel and oxidant, as I said before, and it is converted into a liquid gas aerosol, which means liquid is dispersed, liquid droplets are dispersed in a gas, and this evenly distributed aerosol then enters into the atomizer. So this is our atomizer unit. Effectively, this is the nebulizer unit. This is the solution of the analyte which we placed in a conical flask or in a beaker, and we take the pipe, the inlet pipe of the nebulizer, and dip it in this solution. From there, from this, through this pipe, the sample is injected into the nebulizer to form the aerosol, and this is our atomization unit. This liquid aerosol enters into the atomization unit, where it is heated at high temperature so as to achieve desolvation, vaporization and atomization, or I should say dissociation. Once these atoms, individual atoms in vaporized state are formed, they absorb light radiation, resulting into some excitation, and the wavelength that are being absorbed is and the wavelength that are being absorbed are detected by the detector placed in this machine, and the common detectors are the photomultiplier tubes. So there are two types of atomizers, the flame atomizers and graphite furnace, which are basically a type of electrothermal atomizers. These flame atomizers, they are also called as direct aspiration. Why? Because here we directly lit a flame, and these individual vaporized atoms are directly, aerosols are directly entered into this flame, converting it into individual atoms in vaporized and ground state. Remember one thing, students, we do not excite the atoms during atomization. We only convert them from molecules to individual atoms in vaporized state. We do not excite those atoms. If we excite those atoms with the help of this heat, they will start emitting light, and then it will be an emission spectrum. When we study this atomic emission spectrum, there I'll explain you that the atomizers used in atomic emission spectroscopy are even more intense. They provide even higher energy, because in emission spectroscopy we need to convert the molecules into individual atoms first. First of all, we convert the molecules into individual atoms, then we convert those atoms from ground state to excited state, so that they start emitting light, forming an emission spectrum. But here in atomic absorption spectroscopy, the job is to convert the liquid sample into aerosol, and from aerosol we convert sample into dry vapor molecules, and then those molecules into individual atoms in vaporized state, and those atoms should not be in their excited states. The atoms should be in their ground state, so that with the help of light they are excited. Now we do not excite them with the help of heat. If we excite So that they can be excited by absorbing light, not by heat. So we have to keep this thing in mind. So this is direct aspiration technique, also known as flame atomization. Here we analyze a single element at a time. So you can say this is a disadvantage of this technique as well, because if we have, for example, if we have more than one analyte in our sample, we have to do the analysis number of times, because we analyze single element at a time. Now, as far as the fuel is concerned, we have some flexibility. We may use hydrogen gas, we may also use acetylene, but acetylene is more preferable as a fuel in atomic absorption spectroscopy. And similarly, for oxidant also we have some flexibility. We can use air, we can also use pure oxygen gas, and we all can also use nitrous oxide as an oxidant. Most of the time we prefer acetylene and this nitrous oxide, because if we use oxygen directly for because if we use oxygen directly as an oxidant, there are chances that it may oxidize the sample. For example, if lead is present, it may form lead oxide. So the analysis will get hampered. We do not get the characteristic absorption of lead, because lead has now formed lead oxide. We again then we need to convert that lead oxide again into lead and oxygen. So that is not possible, because that much amount of heat is not available in atomic absorption. So we most of the time avoid using oxygen, just to avoid the formation of oxides. And one more thing, if oxygen is present, it causes flame to be a oxidizing flame. If oxygen is present in excess, it forms the flame to be an oxidizing flame. But in this technique, we do not need an oxidizing flame. We need a non-oxidizing, or I should say a reducing flame for this. So the flame that is being used for direct aspiration, it should not be a oxidizing flame. That flame should be a reducing flame, or we can say non-oxidizing flame. So we have this type of flames that are being formed in this flame atomizers, and these flames have three different zones. This is called as the primary zone, and in this zone we have temperature that is little bit lesser than the temperature we have in this middle portion. This outer portion is called as secondary flame. The secondary flame, although it has a high temperature, but the highest, or I should say the hottest section, is this internal zone, which is present between the which is present between the secondary as well as the primary combustion zones. So we use our sample, so we burn our sample in this particular region, so that high amount of energy is available, and all the sample molecules are immediately converted into vaporized individual atoms in ground state, not in the excited state. So now, while dealing with atomizers, we have to keep two things in mind. There are two terms, the gas flow rate as well as the burning velocity, and we have to keep a balance between these two. If in case the gas flow rate is low while the burning velocity is high, the first condition as it is presented here, if the gas flow rate does not exceed the burning velocity, means the burning velocity is high while the gas flow rate is low, then what will happen? Only small volumes of fuels are injected into the flame. They will immediately burn because the burning velocity is very high. While the fuel is burnt, there will be no fuel that is coming because the flow velocity is low. It ultimately causes the temperature to goes down and the flame diminishes, resulting into flashback. However, if the gas flow rate is equal to the burning velocity, the flame is always stable. High thermal energy is available for atomization to be done. In another case, if the gas flow rate exceeds the burning velocity, which means that large volumes of fuel are injected into the flame while the burning velocity is low, then only a part of the fuel will be burnt, and then the remaining fuel will ultimately blows off the burner. So there should be a balance between the gas flow rate as well as the burning velocity, because if they are in good coordination, they are in good agreement, and there is a balance, then gas flow rate and burning velocity are equal, the flame is stable, high energy will be available for atomization. But in case if the gas flow rate is very high, large volume of sample is introduced, but it will not burn properly, then the unburned sample, then the unburned fuel will blows off the burner. In contrast, if the flow velocity, if the gas flow rate is, in contrast, if the flow rate of the fuel is low while the burning velocity is high, the moment fuel enters, it will burn off, and since the velocity of and since the flow rate is low, there will be limited supply of the fuel and burning velocity is high, so the temperature will not be achieved and ultimately it diminishes the flame, giving flashback. So there should be a balance between the two. Based on the different types of fuels available like CNG and natural gas or compressed natural gas, hydrogen, and the different types of oxidants, we can achieve different temperatures as well as burning velocity. For example, you can see that if we take natural gas as a fuel and air as oxidant, we can go up to temperature of 1700 to 1900, while the burning velocity is only 39 to 43 centimeters per second. While if which, because air is a mixture and mainly contains nitrogen, which is an inert gas, because air is a mixture, and it contains mainly nitrogen, which is an inert gas. On the other hand, if we take pure oxygen, of course there will be some high temperatures can be achieved and the burning velocity is also increased. On the other hand, if we take hydrogen gas, with hydrogen in presence of air as an oxidant, the temperature of 2000 or 2100 degrees centigrade can be achieved, while the burning velocities are also moderate. Similarly, with hydrogen fuel and we have oxidant as pure oxygen, we can go up to higher temperatures as well as higher burning velocity. But when you look at acetylene gas, and that is why, because we can achieve very high temperatures as well as burning velocity, we always prefer using acetylene gas. With acetylene and air, we can go up to 2400 degrees centigrade, but the burning velocity is low. But if acetylene gas is taken as a fuel along with oxygen gas as an oxidant, we can achieve temperatures of over 3000 degrees centigrade. We can achieve temperatures of around 3000 degrees Celsius, and you can see the burning velocity is also very high. So we can maintain high flow rates. The burning velocity is large amount of energy is available for atomization. For acetylene and nitrous oxide also, we can have high temperatures, although the burning velocity is moderate, it's not very high. But in some cases where there is a chance of oxidation of the sample due to oxygen gas, we use nitrous oxide as well. Again, this figure shows the structure of the flame. As I said before, we may have a primary combustion zone, and then we have an outer zone which is called as the secondary combustion zone. If we compare the temperature, we can have, although the temperature is high, but if we compare the temperature of the primary zone with this internal zone or with the secondary zone, the temperature is a little bit lower here. Then in case of secondary zone, since it is the outer zone, if we burn the sample here, there is a chances of oxidation, which we of course we never want to happen, and therefore we prefer this particular region which is called as the internal zone for atomization, because this is the hottest region and the possibility of oxidation of the sample is minimum here. The possibility of oxidation is also minimum in the primary zone, but primary zone has lower temperature. If we go for secondary zone, here the temperature is high, but there is a possibility of oxidation of the sample. So we do not prefer the secondary zone as well, and therefore we prefer the internal zone. You can see the temperature profile of different regions. Even this primary region, at the top of this primary region, we can have temperatures of over 1800 degrees Celsius. While in the secondary region, we can have 1750 and 1800 degrees Celsius. But if you look at the internal zone, the middle zone, in between these two, secondary and in between these two primary and secondary regions, the temperature is highest, over 1858 and 1863 degrees Celsius temperature, and the possibility of oxidation is also minimum, and therefore we prefer the sample from the nebulizer is injected and atomized in this particular region. In the actual flame, this is the region where we atomize the aerosol. You can see in this flame, which is the actual, you can see in this figure, which is the actual representation of a flame. So as I said, this primary zone, here there is a possibility, here in this primary zone, here there is a low possibility of oxidation, but the temperature is not up to the mark which is needed for atomization. In case of secondary zone, the temperature is high, but there is a possibility of formation of stable oxides which do not decompose easily, and it will spoil the whole analysis. And therefore, we always go for this region, which is a transparent region or nearly transparent region. Here we have high temperature as well as low possibility of oxidation. Therefore, we always prefer this interzonal region for atomization in atomic absorption spectroscopy. Then the second type of atomizers are the graphite tube atomizers. These atomizers works as the same way just like we have our flame atomizers, but the difference is that instead of a direct flame, we use electrothermal units here, and these electrothermal units are it is basically a rectangular unit which is made up of graphite. I'll show you the figure. It is a rectangular unit which is made up of graphite. We have one side, the bottom. These graphite tube atomizers are rectangular chambers that are made of graphite. We have two graphite electrodes, one forms the bottom part, the other forms the upper part, and then we have two optical windows here which allows the UV or visible light to enter into this atomizer. Sample is introduced from the top, and with the help of these two electrodes, the sample is atomized here. High temperature is provided up to 3000 degrees centigrade, and since we are not using a flame, we are not burning the flame, we do not need an oxidant, we do not need oxygen gas. Therefore, this even for precautionary measure, we have two inlet units where we can inject some inert gas. We can use argon gas, we can use neon gas. Since argon is quite cheaper compared to neon gas, we inject argon gas which completely make this chamber free of oxygen and which ultimately prevent the oxidation of the sample. And once the sample is introduced in the aerosol form, it immediately burns due to the high temperature of 3000 degrees centigrade, and it is immediately converted into individual vaporized atoms in ground state, and now it is ready for absorption. Therefore, light radiations of a specific wavelength are passed through these optical windows, and here we have the interaction between these individual vaporized atoms and the electromagnetic radiation, and the transmitted light is then detected with the help of our detector. This is the flow sheet of the graphite atomizer. Here we have a graphite tube, here we have a graphite chamber where the aerosol sample is injected, and the light source is giving light in the UV or visible region which passes through this chamber, resulting into some interaction and absorption of light, and the transmitted light is finally detected by the detector. So this is a diagram showing how an electrochemical so this is a diagram showing how an electrothermal atomizer works. So this is the graphite chamber where the aerosol sample is injected, and we have a light source producing light radiation in UV and visible region, and there will be an interaction between the vaporized individual atoms and the light radiations. and while the transmitted light is detected by our detector, from where we can identify the missing wavelengths, and the analyte atoms and molecules can be identified based on that. This is an schematic diagram of the graphite furnace. As I told you just now that it is a rectangular box which is made up of graphite. We have graphite electrode on this side. This is graphite electrode. This is also a graphite electrode. This, and then we are having two optical windows. These are the optical windows. The sample, aerosol sample, is introduced from the top, and an electric discharge is given to the sample, creating a very high temperature of 3000 degrees Celsius, creating a very high temperature of 3000 degrees Celsius, which immediately turns the sample in liquid form, which immediately turns the sample in aerosol form to individual atoms in vaporized state by the process of desolvation, vaporization, and dissociation. Then these atoms are ready, then these individual atoms are ready for absorption. This is the optical path, the light is coming, there will be an interaction, and the transmitted light then falls on the detector to create a spectrum. I hope after attending this lecture, you have got an idea about the concept of atomic absorption spectroscopy and its two main components, the nebulizer as well as the atomizers. In the next lecture, we'll discuss about the light source as well as the monochromator and detector. Thank you very much.